So our next speaker is Bruno Taketani from IQM with a talk on co-designing quantum accelerators. So thank you very much, Bruno, for being here. I think that you can share your screen. Can you confirm that?
No, doesn't seem to be.
So just give me a second.
Yep. So maybe you can tell me if it's correct now.
Right now, I cannot. Okay.
Yeah.
Yes.
Okay.
Now we are perfect.
Very good.
Yeah.
Very good. Thanks.
Finally.
Thank you very much.
All right. Good. Sorry again for this technical things. I should definitely stick to quantum computing. Much easier. All right. So thanks, Lorenzo, Danielle, and everyone involved for organizing and for inviting IQM to come here. Actually, before I get into it, let me just say that it's been really a pleasure. So I've been involved in many discussions with many different people, including several of the speakers from the previous sessions. And it's very nice to see how this is a forum where people are really publicly sharing their ideas, even if their ideas are just problems, which I guess is a fair thing to say for most of us. But it's very good to have this public forum and that to see that people actually take advantage of it. And also, it's very interesting to see how the conversation is converging and we are all understanding that the things that need to be done and what.
Bruno, I beg your pardon. Could you just shut down your video camera because we cannot hear you very well. Maybe it's you have a limited bandwidth.
Okay. My maybe this probably work. Let me then.
So you can do it by using Teams. Just disable the camera. You don't have to change anything else.
Yeah. Yeah.
Okay.
Hi. Can you hear me?
Yes, we can hear you.
Now,
is it fine now?
We need you to go back in the slideshare, please.
Yeah, sure. All good? Hi, can you hear me?
Yes, we can hear you very well.
Yes,
you just need to share the
see
slide.
The proper slide.
Yeah.
Okay, it's in principle sharing already.
By the way, I can see your screen, but not your slide.
You don't see it?
I see your screen, but not the slides. So just open the slide in this desktop and.
Yeah, but in principle it's there. Okay, let me just stop sharing again. This is not going well. You see the slide?
Not yet.
This is.
Okay, fine. I can see the slides.
Oh, perfect. Okay.
You can.
So there's
resume.
Lag apparently. Okay. Yes. So I was essentially saying this is very good. I'm very happy to see, and hopefully you can see my presentation now because it's not. There's so far a lot of technical problems. Okay, so what I want to do today is first of all start off by telling you who IQM is. So I imagine that for some people IQM is new, So describe to you a little bit who IQM is, what are we doing, then tell you what are the products that IQM is working on, which then will directly map into our HPC activities, HPC-related activities. Okay, now I have changed the slide. Can someone confirm that you see a new slide? Just so that I know things are working.
Yeah, everything is fine. We can hear you fine, and we can see your screen.
Okay, good. Thank you. All right, so IQM is a company building quantum computers. We're building these nice-looking boxes, machines here that you see on the corner. And what's inside here is a quantum computer, and this quantum computer is superconducting technology. So we're building superconducting qubits here. Now, who are the people? What's the story behind IQM? IQM is a spin-out, a bit more than 2.5 years old, or almost 2.5 years old now. It's a spin-out from Aalto University and VTT, so it's a Finland-based company. And one of the things that I think that distinguishes IQM from others is that we're really developing our technology quantum computers. So when you come to us, you want to buy them, and we sell it, and then we deploy that system on your premises. To do that, we need certain expertise, also translating to us being towards a full stack company. So we're really going from the chip design, manufacturing. We have our own clean room, the software that runs the system, and even the algorithm design. We have 3 offices, as a matter of fact. So as I said, the headquarters is in Finland, where we have around 100 employees now. But we also have, since March last year, an office in Germany, where I'm located. And as a matter of fact, we also have, I think, for 4 or 5 months already, an office in Bilbao, Spain. It's just not showing this nice graph because we haven't yet, no full-time employees has started there yet, but soon you're going to see populating this year. So I'm not sure whether it's fair to call IQM a startup. We are bordering 100 employees in 3 locations, but still we at least have the startup mindset in the company. Obviously, we are an R&D heavy company, which means we have a lot of PhDs and so on. And this is the people that are building really this technology. Now, in terms of products, what are these on-premises quantum computers that we are developing and selling? Well, you can divide our product classes into these 3 layers here. There's an IQM research side. There's the HPC integration, which of course is the reason that I'm here talking to you today. And then there's also a quantum ASICs. So I'm going to run you through this the systems here, and you're going to see that you're going to understand that the idea behind them a little bit more, and also see how they increase in complexity as you move along. Now, the IQM research, the idea here is really to sell small systems to research centers. That might be a national laboratory, a research center, or a forward-thinking R&D heavy enterprise as well. But here the idea is that we're selling small to a few tens of qubit systems, and then the user can really experience with quantum technology, with quantum computers, either from the high level running quantum algorithms and then trying to figure out how they scale, if they make sense, if they don't make sense, how do they deal with noise, all the way down to working out new pulses to control the qubits and whatnot. And we're very happy because in the end of 2020, we were selected as the winners of a public tender in Finland to deliver Finland's first quantum computer at the installations of VTT. Now, that is a very good opportunity for us to develop our technology and to deliver. And the process goes into 3 phases. There's an educational phase where we deliver a 5-qubit, this is this year, a 5-qubit QPU. This was already done. The whole system has been set up. The QPU has been delivered, has passed all the tests. This phase is now concluded, maybe a month ago or so. And then the next phase comes next year, where we then upgrade the qubit, the QPU from the 5-qubit one to a 20-qubit QPU. And then in 2023, we move to a 50-qubit QPU there. Now, the HPC integration side, well, that is the one that's more interesting here to this audience. And I think it's obvious enough what we could mean in this point. So I'm not going to talk about it now. I'm going to move to the next step, and then I'll come back to the HPC integration, where obviously I will focus during this presentation. Okay, so the quantum ASIC side. The idea here is, and this is just a very high-level explanation, I'm not focused on this today. The idea here is that we're going to develop quantum processors that are tailored really for specific applications. And why we do that is because by tailoring the processor for that specific application, we can reduce significantly the resources that need to be built into that processor, and thus simplifying it. By simplifying it, we can deliver quantum advantage sooner. So the idea is really to have these quantum ASICs to speed up and get a shortcut to quantum advantage. This is one of the core systems at IQM, but again, since this is an HPC-focused crowd, I will not be talking more about it, but feel free to ask me questions later. Now, after hearing the previous talks, particularly yesterday in the afternoon, I was wondering whether I should talk about this slide. So I reformulated a little bit of my talk, but particularly this slide, I was looking at it for a while, and I was thinking, well, it seems like I don't need to preach to the converted. But on the other hand, well, I think the conversation is still too nascent on this idea of HPC integrated quantum computers that it is still worth to repeat the message. So bear with me, because you've heard this already, but let's see from the academic perspective, what's the idea here? Why do we need HPC and quantum together? So there are several ways of explaining this. The first one is the one that was already mentioned many times, or actually both already mentioned many times yesterday, but the first one is the near-term idea that the first algorithms that are going to have commercially relevant results are going to be coming from a quantum computer accelerating or working in tandem, at least, with a classical computer, and thus accelerating the work of a classical computer, right? And when you think about that, you naturally go to this idea of hybrid algorithms. And here the thing is, well, if we take the fully quantum algorithms that are out there, they are all very deep circuits, meaning that you need to perform a very long sequence of operations in series to then get your output. And because of the quality of the devices at this current stage, we know that this is not doable. We are limited to what we call shallow circuits that only have a small number of operations that you need to perform in series. Now, the idea of hybrid algorithms is that you can take a full complex quantum computation and actually break it down into a smaller quantum computation, which happens in a shallow circuit. And then you offload part of the work to a classical computer, and you put these two to work in tandem in a loop until your result converges to the desired outcome. Now, if you think of it like this, you will immediately say, oh, great. Then it means that the first applications, I should have my classical computer, my quantum computer working in tandem with a classical computer. Whether that classical computer needs to be a high performance computing system or not, well, that is another argument that we can go into, and Mikael Johansson was making good points yesterday about that. But definitely what you want to do is you want to optimize your system to work in close tandem with classical systems. But again, this is really the near-term vision. If you think of the long term, we have to remember that quantum computers actually are very good at a limited amount of tasks. So far, we only have a handful of algorithms and then extensions of those, meaning that we don't have too many applications. The applications that we do have are powerful, but it's not that many. So you can expect that in the future, if the scenario doesn't change, a user will have a complex computation that they need to implement, and only parts of that computation can take profit of quantum computer. Only parts of them are amenable to quantum advantage. So just like it happens with GPU that we are mostly using to date, we're mostly using for the majority of problems, CPU for the computation, then we offload parts of that computation to a GPU. In the same way, you can think that this is going to happen to quantum computers. So the user still needs HPC systems, and then parts of their computation goes into a quantum computer. In that scenario, yes, we still need to have a the tighter the better integration between the HPC and the quantum computer. Now, what are we doing at IQM? Well, obviously the goal that we have, now I come back to this product plan, is to tailor our product to the HPC market needs. And that is, albeit an obvious sentence, is one that can give you pause to reflect a little bit of what it means. If we want to adapt to the market needs, that first of all means that we need to talk to, well, everyone involved. We need to talk to the end user that might need HPC and quantum resources to understand how they want to work with those. We need to talk to the vendors of HPC systems to understand how their process is, how they build their systems. We need to talk to the HPC centers that host the systems so that we understand what are their limitations, what are their concerns regarding the quantum computers. So our work is really to talk to a lot of them and build the solutions together. That's very critical for IQMs, that we're working with our partners to build it, as I'm going to showcase in the next few slides. And then what are some open questions that we're trying to understand? Well, I think at this stage, honestly, we have to pause and remember that, I don't know, I'm going to say that maybe 2-3 years ago, nobody was talking about this topic. So we're still at a stage that the conversation on HPC and quantum is new, that the investigations are few, especially publicly available results are few. So we are still at a stage that we are identifying questions. And I saw that very clearly yesterday. It was really nice to see that in several of the presentations. So from the IQM perspective, some of those questions are, for instance, what are the possible problems that we might have when we want to take our quantum computers, our quantum accelerators, and put them side by side with a cluster system? There are many problems that might occur. What would those be? What would be workarounds to avoid those problems? How far do we push our efforts into adapting our systems, hardware and software-wise, to the HPC facility? Sometimes it's going to make sense, sometimes it's not. What are metrics that we can use to define when does it make sense to go in a direction or another one? Then another discussion that really often pops up is the standards. Do we need standards already for the interface between the systems? And at first, when I was faced with this question, I was thinking, no, this is too new. We are still, if we put standards now, then we just might find ourselves boxed in a corner developing technology that's not the best thing just because it's the standard. On the other hand, we have seen in the past technology that suffered on their development because the standards were not defined, because different people were developing different things on different directions. And then if you work with system A and B, and then you want to work with system A and C, you cannot do that because, well, A doesn't talk to C anymore. So maybe we need to avoid that, and maybe we do need to talk about standards, not necessarily defining them now, but at least understanding where the standards would be So this is a conversation that still needs to take place. And again, it needs to involve all the stakeholders there. And then at IQM, what we're doing is we're currently focused on the software level, really trying to come up with the solutions, the architectural solutions for the integration. And then, as I pointed to hybrid algorithms in the last slide, really optimizing those to the implementation of hybrid algorithms. And of course, the idea again is always to maximize the uptime of the systems, which might mean, for instance, offloading part of the work that the quantum computer has to do to the HPC. So what would be the functions that we would offload and why? How do we define that? So those are the lines of questions that IQM that we are working at IQM. And what are the paths that we have taken in that direction? I would say it all started just a few months after IQM actually kicked off, where IQM, CSC, and Atos formed a partnership where CSC is holding a QLM from Atos, they're hosting it, and then they're providing access to IQM, to the system, and it has proven to be a very integral part of our R&D tool set. And through that, we have also initiated discussions of integrating actually our quantum computers to the Atos QLM, which could then be used as an execution environment for the user to run algorithms and experiments on our QPU. Following that, last year, I think it was already the end of last year, that we were selected by the German Ministry of Research on a project that we are leading together with Infineon Jülich Supercomputer Center, Freie Universität Berlin, and LRZ. We were selected in this project to place one of our QPUs on the facilities of Jülich and LRZ, and then in LRZ really work on the integration of that system to a small HPC environment. And the idea here is really to give access to the users for our system, 5, a 20, and a 54 qubit devices that will be focused on running something called digital analog quantum computing, which is just a different paradigm for quantum computers. And this project ends actually with the concept and test of cloud access to the systems as well. From that, the bridge was really good for us to then be selected last month, again by the federal government, to lead a project with Atos, LRZ, and HQS here in Germany to actually provide the first gate-based quantum computer integrated into an HPC environment. So the idea here is that this project has a system purchase side and an R&D side. And on the system purchase, LRZ is acquiring a 20 qubit device quantum computer from IQM, full stack, a next generation Atos QLM, and the license for the simulation software from HQS. So here it's really good because you can see that you have from HQS the application, Atos the emulation, and then from IQM the system integration, and we're all working under one roof, under one umbrella, together from end user to hardware provider, working with the HPC Center LRZ to put those things in place and really test the HPC integration environments. What are the best solutions, what are not good solutions, and whatnot. So I really like the idea that this is a joint project. And I think Daniela was making a point yesterday about how good it is that Germany is investing in this. And it really is good. The German government seems to be very focused on developing quantum industry here, and this is a project that will hopefully help a lot in that direction. And just as a side note, we were very happy that we actually hosted here in our offices the minister herself, that came to give us the paperwork for the approval of the project. So I think I'll skip this slide. This is just explaining a little bit the ins and outs of that project. What are we delivering? What are the R&D activities and whatnot? But let me skip that because I still have two things that I want to point to. So first thing is, what do you expect? What should you expect from IQM? So the first thing is that in the first half of next year, we plan to have already operational the first device placed in LRZ, already with basic integration to an HPC system being evaluated and implemented. Of course, we're going to continue our efforts with Atos and developing the integration to the Atos QLM, not only as a simulation tool, but also, as I mentioned before, as a middleware for the full integration to an HPC system. And then what I would like to really highlight here is that we've been doing this and we need to continue doing this. Not only, I'm not saying IQM, I'm saying all of us. We need to have the debate. We need to sit together. We need to sit different parts of the stack together so that we all can talk and educate each other into what it is that HPC quantum integration should mean. What are the different advantages of the different approaches, so that we can really start to build a solution that makes sense for all of us, understanding what each of us needs and what each of us can deliver. These are two very important things. And I think it's fair to say HPC, people from the HPC background don't really know quantum computing. They quickly learn quantum computing from the theory level, but the experiment, how these boxes actually work here on the slide, that's a whole different thing. And in the same way, I think Ariana was making a comment yesterday that when people from HPC talk to quantum physicists, this was a well-pointed argument. You often find resistance in that people from quantum computing think, oh, we don't need HPC, why do we need it? I have to actually admit that I was faced with that same question when I was first thinking about this topic. So we need to continue that conversation. That's really important, which also would lead to the last point there of us eventually sitting and really talking. If we now know what integration means, what are the places, what are the interfaces that we need to have standards for? And then we can start working on those. And now just to close my last slide here, I just want to point out that maybe some of you have already seen that, but this is to kind of, let's say, give backing to the idea that this workshop is all about. So IQM and Atos joined forces and funded a research that was conducted by an analyst firm called IDC, with the goal of understanding from the HPC center's perspective their business and technological challenges. So they had phone interviews with 110 HPC centers. If you want to have a look at the full white paper describing the results, it's available on IQM's website. So just go there, click a few times, and you get it. But this really was a worldwide survey, quite representative, and gave us some really good insight. And here I'm just showing you two of the results that I find more interesting. The first one on the left side here is what is the current and expected level of adoption of HPC, of quantum computing by HPC centers. And it was very interesting to see that about a quarter of HPC centers already have some kind of pilot project, or at least they're developing some business case for quantum computing. But then 49% expect to have adopted such projects in the next 2 years. That means that by 2023, 76% of HPC centers worldwide are expected to have some kind of quantum activities. And that's really promising for us as an industry, but it also means that we have to get going. We have to do our work. People in this workshop need to do, we all need to do our work so that we develop this technology in the best way possible. And then the other result, which now is really speaking to IQM's choice of business model here, is that what is the type, the question is, what's the type of deployment model that you expect, that you have currently, or you expect to have in 2026 for quantum computers? And the options were, for 2021, let me go with this. On-premises, for those that use quantum computing already, 7% said they use fully on-premises quantum computing, 70% mostly cloud-based, 23% mostly on-premises, and some cloud access. And it's very interesting to see that in 5 years' time, actually the majority of the HPC centers actually believe they're going to be working mostly with on-premises solutions rather than cloud-based. So this is quite interesting. It raises all sorts of different questions, and from the IQM perspective, it's very good to see this number because that's our business model. We develop and sell quantum computers to be placed on the premises. So with that, let me thank you for your attention. Sorry for all the technical challenges that I had. Let me also say that we are hiring, let me shamelessly say this. So from the HPC side, from the quantum computing side, from electrical engineering, cryogenic engineering, just have a look at our website and feel free to contact. Thank you.
Thank you very much, Bruno. We have a question from the chat. So could you please at a level explain IQM quantum accelerators architecture? Is it like Qiskit runtime?
Yeah, that's a very good question. In some aspects, it is like Qiskit runtime. So we do have, if you're talking about the hybrid algorithms approach, you do have this issue of running the variational calculus locally being far more efficient than sending this back and forth to the user. So the user can just run, can just send the entire system, the entire code that they want to use. But it is more involving than that. We're trying to work not only on the side of variational algorithms, but also on more general algorithms as well.
Thank you very much, Bruno. So we will have a short coffee break. We will resume at 15:45.
All right, thank you.
Thanks, Bruno.
Very good. Thank you, Lorenzo. See you in 15 minutes.